In earlier tapes in this series, we discussed the protective schemes that are used on generators, transformers, buses, and large motors. In this tape, and the next one, we'll be looking at protection for the lines which connect all of this equipment together. First, distribution lines. The distribution line runs a distance of typically 10 to 30 miles. The conductors may be delta connected, that is, with no neutral, but more often than not they are Y connected with a neutral running along the same support structures. The loads across the three phases are often out of balance, so that some current normally flows along the neutral. The neutral is usually connected to ground at the source transformer, and additionally by connection to the grounding straps, which run down intermittent poles into ground. By far, the most common way of operating a distribution line is by a radial connection, like this. The line is supplied from a source at one end only, and loads are tapped off to feed the customers all along the route. Current flow is in one direction only, even under fault conditions. Sub-transmission and transmission lines which carry higher voltage are usually supported on steel towers, although wood structures are still used in some instances. Only 3 conductors are run as the load is considered to be balanced. Usually a grounding wire is connected along the top of the tower, both to act as a shield against lightning and also as a conductor for ground currents. The foot of each metallic tower is also grounded through a grounding rod. The sub-transmission line may be connected radially, that is, one line to supply one distribution substation, but more commonly it is connected in a loop arrangement like this. Here we have one source of supply feeding into a loop which may cover a total distance of, say, 50 miles. At various points around the loop, distribution buses are located. In some systems, large industrial consumers are fed directly from this sub-transmission system at high voltage. The advantage of the loop is that in case of a fault, say here, this faulty section of line can be isolated by opening the breakers at each end, while the loop continues to supply the remainder of the customers. In some loop systems, a further source of supply may be added so as to increase reliability. The sub-transmission lines provide the link between the high-voltage bulk transmission system and the various distribution stations. The high-voltage transmission lines usually cover long distances, perhaps up to 500 miles or even more, bringing power from remote generating sources to the areas of load demand. High-voltage transmission lines are also used to interconnect with other power systems, both to supply energy or import energy when needed. For long-distance lines, a very approximate rule of thumb indicates that the voltage should be about 1 kV per mile. Transmission lines normally form part of a complex network which interconnects many lines and buses and also includes several sources of power generation at different locations. As with the loop system, the current in any particular line can, in most cases, flow in either direction according to the configuration and loading of the system. All of this adds to the complication of providing adequate protection, as we shall see. Now, what are the types of faults that can occur on lines? Don't forget that in addition to overhead lines, power can be transmitted on underground cables. Actually, because of the physical protection, underground cables suffer faults quite rarely. One problem can be damage caused by construction machines, perhaps digging into a cable and causing a short circuit. An underground cable could also suffer from insulation breakdown, perhaps due to faulty manufacture, or maybe due to extended periods of overload. In most of these cases, the result will be a short circuit between phase conductors and phase to ground. The vast majority of circuits are in the form of overhead lines, and in this case the most common fault is a flashover caused by lightning. The extremely high peak voltage of the lightning stroke causes a flashover of the line insulator to ground, and once this is started, the fault current will continue to flow even after the lightning stroke is passed. This phase to ground fault will remain as long as power is being supplied to the line. If two conductors are affected by the lightning stroke, then we would have a phase to ground fault. Clearing the fault is important, not so much to prevent damage to the line as to prevent damage to the equipment, that is, generators and transformers, which are supplying power to the faulted line. The protection scheme must be designed and set so as to trip the breakers feeding the faulted line, but to leave the remainder of the system operating intact. You will remember we have already discussed in earlier tapes the need for sensitivity and selectivity of protection schemes. A fault due to a lightning stroke is temporary in nature, because as soon as the circuit breakers are opened, the fault disappears. For this reason, reclosing arrangements are used on the vast majority of lines. This may take the form of a reclosing relay on the feeder breaker, or a recloser switch which is usually installed out along distribution lines. If the fault is a permanent fault, then the breaker will open again and the recloser or reclosing relay will lock out so as to leave the line isolated. So what could be the nature of a permanent fault on an overhead line? Well, one example is the collapse of the line as a result of hurricane or tornado damage to towers. Another weather-related possibility is the formation of heavy ice, which may stretch the conductors and perhaps cause eventual breakage. Another possibility could be, say, an aircraft or other object coming into contact with the conductors. All of these scenarios causing permanent faults are rare and unlikely occurrences. However, on distribution lines, a fairly common cause of a permanent fault is when the branches of a tree fall into contact with the conductors, causing a phase-to-phase or phase-to-ground fault. Now, bearing in mind all that we have said, it is obvious that the type of protective scheme chosen will depend very much upon the installation itself. For example, it is certainly far more simple to protect a single radial distribution line than a transmission line which forms part of a complex network. Moreover, the isolation and outage of a transmission line may cause interruption of power to many, many more customers than the outage of a single distribution line. Backup protection is important so that if the primary protection fails to clear the fault, the backup will take over and operate after a short time delay. In all situations, the objective is to provide protection which is sensitive, selective, and reliable. We'll be looking at the various line protection schemes as we proceed through this tape. For now, let's take a break. Please switch off the tape and review the material in your workbook. Overcurrent relays are widely used for protection throughout the distribution system and in many sub-transmission systems. The time overcurrent relay is very suitable for the protection of radial lines where the fault current flows in one direction only. The inverse time characteristic allows faults downstream to be cleared by local protective devices, usually fuses, before the relay has time to operate. This prevents the relay from opening the breaker, so interrupting all of the customers on the line. On the other hand, if the local protection fails to operate, then the time overcurrent relay would eventually time out and open the breaker to clear the fault. Thus, it acts as remote backup to the downstream local protection. As we noted before, operation of remote backup protection causes an outage to many more customers than local protection. Ideally, 3 CTs and 3 overcurrent relays will be installed and connected like this, 1 per phase. An additional relay can be connected to measure any residual current and so detect ground faults. In some installations, one of the phase relays is omitted for economy. This arrangement will still detect phase-to-phase and phase-to-ground faults. However, if a phase relay fails in this setup, there is no backup. In setting the time over current relay, we must make 2 adjustments. 1, the pickup value, that is, the point at which the relay starts to operate. And 2, the time dial setting, which defines the time of operation for different values of fault current. The time characteristic is often shown on the single line diagram like this, with the vertical axis representing time in seconds. With a fault close in to the breaker, the magnitude of fault current will be highest, and consequently the time delay is the shortest. In setting the relay pickup, we need to take into consideration the value of short-term maximum load current. For short-term load, it is usual to consider the average over a period of 15 minutes to 1 hour, not the instantaneous peaks. The relay should obviously be set with a reasonable margin above that average. In addition to maximum load current, we must also allow for any magnetizing inrush current to feed the transformers along the line. We must also allow for cold load pickup when the line is switched in. Typically, the pickup of the phase over current relay is set to about 1.5 to 2 times the short time maximum load current. The ground relay is usually set to about half that value in order to keep the pickup as low as possible. We'll be talking in more detail about ground fault protection later in this tape. In order to set the time dial of the relay, it's necessary to know the anticipated value of fault current for a fault close into the breaker and for a fault at the far end of the line. As we know, the level of fault current flowing to feed a short circuit at the far end of the line will be less than for a short circuit close in. This is because of the impedance of the line between the 2 points. There is also another factor which may affect the level of fault current, and that is the amount of fault capacity which is available at the source. What do we mean by this? Well, in periods of high load demand, we could have many generators and parallel circuits feeding into the system. This will provide high fault capacity and low impedance. Conversely, during a period of light load, some of the generators and circuits may be disconnected, so we'll have lower fault capacity. The result is that during light load, the level of fault current at any particular location may be lower than at peak time. This effect is more noticeable on loop-connected systems rather than on radially connected distribution lines. Normally, fault studies are carried out by your company's engineering department to provide maximum and minimum levels of fault expected at each location. When setting the time dial, we have to take into consideration the minimum level of fault current at the end of the line. We do not want this fault current to flow for an extended period of time and cause damage. In practice, other protective devices such as reclosers and fuses are usually installed along the line, and these are sized for the amount of current flowing in that part of the line. For example, the recloser usually has several settings. The first is instantaneous, 1 time only. The second and third setting have time delay. The fuse is usually rated at 125 to 150% of the short time maximum current. Let's look at an example. This transformer is feeding a radial distribution feeder, which itself supplies several load centers. All of these protective devices, the fuses, the reclosers, and the breaker overcurrent protection, need to be coordinated. First, to protect the transformer from damage due to overload, and secondly, to provide selectivity in isolating the faulty circuit only. For example, a temporary fault out here would cause the recloser to open on its instantaneous setting. It will then reclose after a short time interval, say 3 seconds. However, if the fault were permanent, the recloser would open again, but only after a time interval. However, before that time, the local fuse will operate to isolate the faulty circuit, so the recloser remains closed. This particular branch has no recloser, so a temporary fault out on this circuit would cause the instantaneous overcurrent relay to open the feeder breaker. After a time delay, a reclosing relay would cause the breaker to reclose. After this one reclosing, the instantaneous overcurrent relay is prevented from operation again until a timer times out, usually several seconds. If the fault is permanent and remains on, then the fuse will operate to clear the circuit. Okay, so let's take a closer look at the coordination requirements for this circuit. The characteristics of the various protection devices are plotted on the log-log scale. This shows current along the base in amps and time in seconds along the vertical axis. We are concerned about protecting the transformer, so the first thing to plot is the transformer damage curve. We must make sure that all of the protective devices operate on this side of the transformer damage curve. At these two locations, 65-amp fuses are installed. The characteristic of the 65-amp fuse is shown on the curve. As an example, this indicates that a current of 1,000 amps in this particular circuit will cause the fuse to melt within about 0.3 seconds. This is long before the high current can cause any damage to the transformer. The same applies to the 100-amp fuses located at these two branches. The fuse characteristic is shown here. Let's take a look at the recloser. The minimum trip rating base fault is set at 560 amps. This is just over twice the normal load current at this point. The first trip, that is instantaneous, will trip before the downstream fuse has time to operate if current is above pickup. It will reclose again and wait for the second trip, which is time delayed. The curve is shown here. Now the pattern becomes clear. The recloser still operates in good time to protect the transformer, but it allows the fuses to operate first for downstream faults. If the fuse does not clear a permanent fault, then the recloser will remain open after the third trip and so protect the transformer. If this fails to clear, that is, the recloser remains closed, then the time overcurrent relay on the feeder breaker will operate. This is set for minimum pickup of 720 amps, which is just over twice the maximum load current. The time dial is set so as to provide a time delay of at least 0.2 seconds over the recloser. There is yet further protection if all of these devices fail to operate. The fuses on the high voltage side of the transformer. The transformer maximum capacity is 25 MVA. On the primary side of the transformer, this will result in current of 25 MVA divided by √3 times 115 kV. This is equal to 25,000 divided by √3 times 115, which equals 125.5 amps. Because of the short time overload capability of transformers, the selected fuse rating should be equal to or greater than the transformer full load rating. In this case, a fuse rating of 125 amps is installed. In order to compare the primary fuse characteristics with the other protection devices, we must convert the primary current into secondary values at 13 kV. Each current value must be multiplied by 115 kV and divided by 13 kV. The characteristic is shown here on the curve. Once again, good coordination is provided. The high voltage fuse protects the transformer, but it will only operate if the downstream devices fail to clear the fault. One important point to notice here is that two curves are shown for the primary fuse. One is the maximum clearing time for any particular current, while the other shows the preheat minimum melt current. Why do we need this? Well, suppose we had a fault, say here, close into the breaker, and the breaker was slow in operating to clear the fault. The high voltage fuse elements would start to melt and become damaged. Before the fuse element melts open, the breaker may eventually open and clear the fault. So now we have a damaged fuse that next time round will probably blow in a very short period of time, long before operation of any of the downstream protection devices. This will isolate many more customers than necessary. In checking coordination circuits, we must always use the pre-melt curve. For now, switch off the tape and review this material in your workbook. As we mentioned before, a loop arrangement is generally employed in sub-transmission systems and even in the distribution system on occasion. In its simplest form, there is only one source of supply, and the loop is often split, usually at the far end. In this case, we have effectively two separate radial circuits, and the protection coordination will be similar to that which we have just looked at in the previous segment. However, in order to provide increased reliability, the loop may be operated fully connected so that current flows in either direction around the loop, depending upon the magnitude of the load at different locations. In a sub-transmission loop, breakers will be located at both ends of each section of line feeding into the various buses. Now, if a fault were to occur, say, at the very end of the loop, at this point, current flows from the source to the fault in a clockwise direction along the upper part of the loop, and in a counterclockwise direction along the bottom portion. The overcurrent relays are set up to be directional with the tripping direction looking into the line. For example, for these breakers, 3, 4, 5, and 6, the directional element will trip in a clockwise direction. At breaker number 2, there will be no need for directional control, as fault current will always flow in one direction only. Similarly, breaker A does not need directional control. However, breakers B, C, D, and E need to be set up with their directional control in the counterclockwise direction. The coordination of the relays must be performed in two stages. That is, first the clockwise loop, and then the counterclockwise loop. For the sake of clarity, we can lay out the clockwise group of breakers in a line like this, starting at breaker 2 and working our way through breakers 3, 4, 5, and 6. For this part of the study, breaker A is assumed to be open. The coordination curves of the time overcurrent relays are shown here. The fastest operation is breaker number 6. As we approach the power source, each relay would be set up with a longer time delay so as to allow the farthest relay to operate first and clear its faulty section of line. For example, look at a fault at the end of the line. If breaker 6 fails to open, then the relay at this bus location will open breaker 5 after the additional time delay. This time interval between relays at each specific location is known as the coordinating time interval. Generally speaking, the coordinated time interval is set to 0.2 to 0.3 seconds. The minimum pickup of the relay is set, as pointed out in the last segment, at 1.5 to 2 times the short-term maximum load at that part of the circuit. Once the coordinated settings of the clockwise group of relays have been completed, the exercise must now be repeated for the counterclockwise loop. In our example, this would be breakers A, B, C, D, and E, assuming that breaker 2 is open. Both sets of coordination curves can be shown on the line diagram like this. The upper group refers to the clockwise loop and vice versa. Finally, operation of the whole protective scheme should be checked by assuming various fault conditions. This would include all breakers closed on the loop and the application one at a time of a fault at each end of each section of line. The calculated values of fault currents should be used for both maximum and minimum operating conditions. This study may bring to light certain minimum conditions that perhaps do not operate the relays as desired, thereby necessitating a re-examination of the relay settings. Another potential problem is a backup relay that operates too soon and therefore trips out a larger section of the line than would be necessary to clear the fault. To overcome this problem, it may be necessary to slow down the operation of overcurrent relays close to the power source in order to provide the required coordinating time interval. But this means the relay may be too slow to adequately clear close-in faults in its own section of line. The best method of resolving this problem is to install an instantaneous relay set to reach about 70% along its section of line. This means it will trip the breaker instantaneously for line faults which occur up to this point, but it will not operate for faults at the end of the line. We certainly do not want it to overreach and trip for faults in the next section of line. This would cause complete miscoordination. Setting of the instantaneous relay is complicated by the high transient current which exists at fault inception and is determined by the system's X/R ratio. At the instant the fault occurs, the relay may see up to the square root of 3 times more current. In practice, the relay setting is increased so that the relay's instantaneous unit will not overreach its intended set point. For example, on 345 kV applications, the setting is increased by up to 1.5 times. Looking along the line, the set of coordination curves would look like this, where instantaneous overcurrent relays are installed in addition to time overcurrent relays. Clearly, the biggest improvement in relay operation is close in to the power source. The reduction in time for a fault at this location is significant. There is another incidental advantage. The upstream time overcurrent relays can now be coordinated with the downstream instantaneous relays. Thus, the new coordinating time interval is this distance here. So the time curves can be lowered with lower time dial settings, thus reducing tripping times. Where the loop has several sources of power supply, the problem of coordination of overcurrent relays becomes far greater. Particularly problematical is the difference in conditions between maximum and minimum load periods. For example, during minimum load, some of the power sources may be completely disconnected, and this will probably bring about a complete change in direction and magnitude of flow of fault current. For complex systems, such as found on transmission networks, the overcurrent relay is really not adequate, and other types of protection are used, such as distance relays. One definite limitation of the overcurrent relay is that it is sensitive only to current and does not respond to other parameters, such as voltage, for example. But as we know, in case of a severe fault close to the power source, quite often the voltage falls to a very low level. As a result, the level of fault current may be below the pickup setting of the overcurrent relays. One type of overcurrent relay, the voltage restrained or voltage controlled relay, does take account of voltage as well as current. Depending upon fault calculations, the pickup of this relay is often set to a current level which is actually below normal maximum load current for the circuit. As long as voltage is normal, the relay will be restrained from operation. However, if the voltage falls to a predetermined level, say 70%, the restraint is lifted and the overcurrent element is released for operation. Please switch off the tape and review this material in your workbook. The most common form of protection against ground faults on a line is by the use of overcurrent relays, both instantaneous overcurrent and time overcurrent. The ground overcurrent relay is usually connected like this. If a ground fault occurs on one of the lines of the three phases, a high current will flow along the line to feed the fault. The CTs are Y-connected. Therefore, the difference in current flow along the three phases will be registered by the overcurrent relay, which is connected in the common neutral. It is really measuring zero-sequence neutral current. In setting the pickup for this relay, we must bear in mind the type of circuit in which it is installed. For example, if this is a radial distribution line, then it is probable that there is a certain amount of unbalanced load during normal operation, resulting in current flow through the neutral. Obviously, the relay pickup must be set above this value. On the other hand, there is no need to set the pickup above the level of load current flowing through the conductors, as is the case with a phase relay setting. In order to accommodate these factors, the relay is usually set to operate at between 25 to 50% of the circuit's short-time maximum current. The situation is different where the ground overcurrent relay is installed on sub-transmission or transmission lines. Generally, in these circuits, the loading across the three phases is balanced. Therefore, the relay can be set to a much lower pickup, usually around 10% of the maximum current. In a loop system or complex transmission system, the ground overcurrent relays are normally controlled by directional units. The relay will be allowed to operate when ground fault current is flowing into the line, but the directional element will block tripping if the fault current is flowing out of the line into the next section. This is correct. We need the local breakers to open, but the remainder of the system should remain energized and in operation. We spent some time discussing directional overcurrent relays in an earlier videotape in this series. Perhaps at this point it would be worth your while to review this subject in PSP2, Segment C. As we've learned, for the directional unit to operate, a reference or polarizing quantity is required. For ground fault relays, the preferred method is by current polarization obtained by locating a CT in the supply transformer grounded neutral, like this. From a protective relaying point of view, this is known as a ground source. The circulating ground fault current will flow up the neutral to continue feeding the fault. you will remember that the value of this current is actually the sum of the zero sequence currents in each line. These zero sequence components are all of equal magnitude and are all in phase. This value is often written as 3 times I0, that is 3 times the zero sequence current in one phase. The relay compares the direction of this current in the neutral with the direction of current feeding into or out of the line. When the fault current is into the line, and it also returns up the neutral, the overcurrent relay is allowed to trip, providing that the magnitude is above the pickup setting. Transformer tertiary windings are also used sometimes as polarizing sources. These simple methods of current polarization are not always possible. For example, the neutral of the transformer may not be grounded, or if we are dealing with the delta connected side, there is no neutral available. In these circumstances, the directional relay would be polarized by voltage, and this is usually obtained from a broken delta connection like this. We have seen this arrangement before in this program. When there is no fault on the line, the sum of the voltages in the secondary will be 0, as the 3 phases balance out. However, when a ground fault occurs on one line, the voltage coil will measure the sum of the zero sequence voltages, which are caused by the out of balance. This can then be used as reference for the directional element. However, this method does have certain limitations and is therefore not always applicable. Why is this? Well, when a ground fault occurs, the zero sequence voltage is maximum at the fault, but is close to 0 at the supply transformer, the neutral of which is solidly grounded. This diagram shows the voltage profile. Remember that the relay is located here at the beginning of the line on bus G. One way around this problem is to utilize as a polarizing source the negative sequence voltage instead of the zero sequence. You'll remember that during a ground fault, negative sequence voltages are created. As shown on this curve, they are lower in magnitude at the fault and fall close to 0 at the source. However, at the location of the relay, the negative sequence voltage is generally, but not always, higher than the zero sequence voltage. This really depends upon the location of the relay and the characteristics of the circuit. A careful analysis would have to be made before applying this method. The negative sequence voltage is obtained from VTs and by connecting the appropriate filter circuit to the relay. Because of the vital importance of polarization in the operation of directional elements, many ground relays are polarized from 2 sources. In this arrangement, there are 2 separate directional elements, one polarized by current and one by voltage. These elements operate in parallel so that either one can release, that is, permit the overcurrent relay to operate. Negative sequence components are also used to overcome the problem of mutual inductance. Now, what is this mutual inductance, also called mutual coupling? Well, a typical example would be where we have, say, 2 230 kilovolt lines strung vertically on either side of a single tower. The 2 lines are strung fairly close together, so that there is some magnetic coupling between them. During normal operation with balanced loading, this should not cause any problem, as the inductance tends to cancel out across the phases. However, if a ground fault occurs on one line, then zero sequence current will flow in all 3 lines. These will be of equal magnitude and all at the same phase angle. The result of this imbalance is to induce current into the adjacent line. Let's look at an example. Line 1 runs between buses G and H, At each end, the buses are connected to the high voltage side of transformers, which are Y-connected with a grounded neutral. Similarly, line 2, which runs in close proximity, is connected between buses R and S. Now let's suppose that there is a ground fault at the far end of line 1, close to bus H. The zero-sequence fault current will run along the line down to the fault, to ground, and up through the neutral at bus G. Similarly, at the other end, even though the distance is short, the fault current will flow from bus H into the line, down through the fault to ground, then up the transformer neutral to bus H. In both cases, the polarizing current in the neutral and the overcurrent feeding into the line is in the tripping direction. The directional overcurrent ground relays at G and H will trip the breakers at either end of line 1 and so clear the fault. However, while this is going on, a high value of zero-sequence current will be induced into line 2, and it flows in the opposite direction. In this case, out of the line at bus R, down the neutral, through the ground, returning up the neutral at bus S, and into the line at that end. The directional relay at bus S is in the tripping direction. But what about that at bus R? Well, even though fault current passes down the neutral, it will still allow tripping because the current flow through the line is in the out direction at this point. Therefore, the two breakers on this line may be tripped quite incorrectly because of a fault on the other line. The problem of over-tripping due to mutual induction is difficult to analyze. In any situation, many factors, including circuit spacing, line length, open breakers, and so on, must be considered. The location of grounding rods and mats, as well as ground resistance, is also involved. The problem at bus R is the reverse direction of current in the neutral to ground. Perhaps the directional elements would operate better if we had voltage polarization instead. However, if zero-sequence voltage was measured and used at this point, it would still allow tripping, because zero-sequence voltage would be induced into the second line. Remember, zero-sequence components are all in phase, while the negative phase components are equidistantly spread across the three phases. So the magnitude of induced negative sequence voltage is extremely low, and therefore should not interfere with voltage polarization using negative sequence components measured on line 2. Of course, application of negative sequence polarization would not prevent opening of the breaker at bus S, because here the current is actually entering the line, that is, in the tripping direction. In this particular scheme that we're studying, another method of preventing breaker R from opening would be by paralleling the neutrals of the transformers at R and G to a common ground connection, if they are close enough together. The current passing up the neutral would be greater than the induced current passing down the neutral, and therefore polarization of the directional relay at bus R would be correct. Another solution is to use mutual compensation CTs, which remove, that is, cancel the induced current in the CT secondary circuit to the ground relays. The problem of mutual induction must be considered when we're analyzing incorrect operation of relay protection schemes. Many times, the only way to resolve this problem is to set the overcurrent relays higher than desirable. In coordinating and calculating relay settings, all of these many and varied factors must be taken into consideration. For now, let's take a break. Please switch off the tape and review this material in your workbook. On most high voltage lines, particularly interconnected transmission systems, the preferred method of protection is by the installation of distance relays. Let's look at the basic application of distance relays to part of a power system. First, we'll focus our attention on the bus G location. Here, a distance relay is installed to trip the breaker number 1 and also to protect the transmission line between buses G and H. The distance relay measures voltage and current entering the line, and from this calculates the impedance downstream. This is the total impedance, including that of the other transmission lines and circuits and the system load. If a short circuit occurs, say halfway along line 1, then the total impedance measured by the relay will fall dramatically, and this will cause the relay to operate. An important characteristic of the distance relay is that it operates independent of voltage fluctuations. For example, if the voltage falls and the current falls correspondingly, the impedance measured remains the same. The operating characteristic of the relay is shown by the RX diagram here. This diagram is specifically for the Moe-type relay. The relay will operate once the impedance falls within this circle. The first point to notice is that the relay is unidirectional. It will not trip for faults upstream of bus G, as the impedance in this area is outside of the circle. However, the characteristic can be offset to allow tripping immediately upstream if desired. Another important point is that the relay trip point is at a higher impedance when its phase angle is at this point, 70 degrees, than for a position, say, here, when the impedance angle is only 20 degrees. This is not coincidental. The 70-degree angle approximates the relationship between reactance and resistance of a high-voltage transmission line. With a short circuit occurring on the transmission line, all of the impedance would be represented by the line impedance, that is, at an angle of about 70 degrees. We can plot on this same diagram the actual impedance of the line between buses G and H. Furthermore, we can go on to plot impedance of the lines farther downstream, that is, between H and R, and buses R and S. Note that the line impedances may not be identical due to different construction techniques, types of tower, and so on. Note in this diagram that the relay setting does not extend to the full length of the first transmission line. That is, it does not reach bus H. So, in fact, not all of the line is protected. Why is this? Well, the main point is we do not want this relay on bus G to trip for faults on the transmission line 2, that is, between buses H and R. Therefore, in order to allow for any impreciseness in actual operation of the relay or the power system, Zone 1 is set to operate up to about 80% of the line. The relay is also equipped with a second element, Zone 2, which is set to cover a longer distance. It will operate for a fault occurring along line 1 and into the first 20 or 30% of line 2. This is set with a time delay, so as to allow the Zone 1 element to operate first. However, for a fault within line 1, if the Zone 1 element fails to operate for any reason, then the Zone 2 element will pick up and operate. It will also operate for a fault for the remaining 20% of line 1, and it will operate for a fault in the first part of line number 2. However, the time delay should allow the local protection at bus H to operate first in order to protect line 2. The coordination diagram here shows Zone 2 stretching from bus G and into line 2. Similarly, the relay is equipped with a third zone of protection, which stretches into line 3. This is set with yet a longer time delay. At bus H, we'll have a similar distance relay installed to operate breaker number 3 and protect line 2, and again on succeeding buses. But what about breakers 2, 4, and 6? In this case, we want the relays to operate for a fault in the opposite direction to that just studied. For example, at bus R, a distance relay will be installed to measure voltage and current entering transmission line 2 through breaker 4. The zone settings will be similar to those we have already looked at, but in the opposite direction, of course. Now, for example, if a fault occurs 50% along transmission line number 2, the distance relay at R, first zone, would trip out breaker 4 without time delay. At the same time, the distance relay at bus H would trip out breaker 3 without time delay, so clearing the fault. If the fault occurred, say, closer to breaker 3, that is within the first 10% of the line, breaker 3 would trip without time delay, and breaker 4, zone 2, would trip after a short time delay. We can superimpose the circle diagram for the distance relay which is installed at bus H to operate breaker 2. All of these diagrams are included in your workbook so that you may give more time to study them in detail. Unfortunately, most of our high voltage protection is not that easy because the system is more complex. For example, it is probable that at bus H there will be additional transmission lines connected, some of which may be connected to other power sources. Let's now look at the case where there is a fault, say 20% along line 2. This just falls within the protection area of zone 2 of the distance relay at bus G. However, in this situation, current is also feeding into the fault from line 3, as there is a power source connected. The result is that slightly less current will flow along line 1 to feed the fault. So the impedance relay will sense that the fault is of higher apparent impedance and therefore farther out along the line, probably outside of the zone 2. Therefore, this relay would no longer provide backup for this particular fault. This condition is known as underreaching. The relay thinks that the fault is farther out and beyond its reach, and it does not operate. Another problem occurs where the lines out of bus H, for example, are of different lengths. In this example, once again, consider the distance relay at bus G. Its zone 2 is set to trip for a point 50% along transmission line number 3, that is 100 miles from bus H. However, line number 2 is a short line of 80 miles in length from bus H. You can see the problem. The relay at G reaches beyond line 2 and into line 4. This will probably result in miscoordination with local relays. This is known as overreach because zone 2 of the relay responds to faults way beyond the normal required operating distance. For this reason, zone 2 relay is usually set to operate closer in, say 20 to 30%. Even the first zone can be difficult to set under certain circumstances. For example, the transmission line may feed more than one bus or terminal, as shown here. The tap to bus R is located fairly close to bus G. The impedance of this portion of the line, here, is only 2 ohms, while the remainder of the line is 8 ohms. The section of line to the bus R is quite short, having an impedance of only 1 ohm. Now, let us consider the distance relay, which is located at bus G. If this is to cover 90% of the transmission line, it will be set to operate when impedance falls below 90% of 10 ohms, that is 9 ohms. But look, the total impedance from bus G to bus R is only 3 ohms. So the high-speed Zone 1 protection would operate for a fault downstream of bus R, or in other words, it would reach into the feeders here. This would certainly cause miscoordination as the breaker 1 may well open before the local protection had time to operate on the feeders. So the answer here is to set up the protection for the impedance of the shortest distance. That would be 0.9 times 3 ohms equals 2.7 ohms. This is not good either because it only provides high-speed protection for 27% of the transmission line. The remainder would have to be covered by Zone 2 protection with its time delay. Another problem can occur with a tapped line where there is a path for current to flow between the two buses, like this. Now, in the case of a fault at this point, current will flow through breaker 1 and along the line in this direction. But if the impedance of this tapped circuit is very low, current may also feed through the tapped line out through breaker 3 and in again through breaker 2 to feed the fault. In this case, the distance protection relay at breaker 3 would not operate, as it would reckon the fault to be upstream of the line. Only after breaker 1 and breaker 2 had tripped would this protection operate to trip breaker 3. So we can see that multi-terminal lines and tapped lines provide certain problems for the application of distance relays. Generally speaking, these types of circuits are best protected by pilot relays. We'll be discussing this type of protection scheme in the next tape. Distance relays are in widespread use throughout the transmission system to protect against phase-to-phase faults. They are also used for protection against ground faults. Where ground faults are concerned, we have to consider the effect of ground resistance on the measured impedance. The flow of current through the earth will encounter resistance. Furthermore, the arc which accompanies a ground fault is resistive. The effect of all this is 1, to raise the fault impedance, and 2, to reduce the phase angle from, say, 70 degrees, the line impedance, down to perhaps 25 or 30 degrees. Thus, the impedance may well fall outside the operating circle of the conventional Moe relay, and consequently not operate to clear the ground fault. The best way to overcome this problem is to install a reactance relay. Instead of impedance, this relay measures reactance only, and is therefore independent of the fault resistance. If the measured reactance falls below the set point, the relay operates. The set point is shown by this horizontal line. In some relays, 2 zones of protection are provided by reactance measurement, and third zone backup is covered by a Moe element. This Moe element also ensures that the relay operation is unidirectional. We've seen that remote backup protection is provided by careful coordination of the relays. On high voltage systems, local backup is also provided by installing additional protective relays and also by duplicating the tripping circuits of the breakers. I recommend right now that you inspect and review the line protection schemes that are installed on your own power system. Note the settings of the relays and discuss this with your supervisor. Please switch off the tape now and review this material in your workbook.